Hello, everyone. This is the CFRG session, and we'll start without delays because we have quite a busy agenda. So we'll start with the chair slides. So the chairs are Alexei Melnikov, Nick Sullivan, and Stanislav Mishlev, and the CFRG secretary is Chris Wood. So let us just remind you about the important things. So the session has been recorded. We have 2-minute takers, Jonathan Holland and Chris Wood. And here is a note well. Some reminders about privacy, the code of conduct with some links. The mask policy. CFRG is part of IETF, so it is a research organization. It conducts research. It's not a NSDO. So we have our agenda and slides uploaded at the data tracker. And we've got quite a busy agenda. We'll start with the chairs update. Then we'll have one proposal from the chairs about one item for our future work. Then we'll have 4 updates on active CFRG items, and then some talks about some possible future work. Any last-minute agenda bashing? No? Then we'll start with the chairs update. So we haven't got any new RFCs since November, but we've got 7 documents that have passed the research group last call. 3 of them are already in the RFC editors queue. #curve draft is in the queue, and 2 other drafts dependent on it are also in the queue. And we have 4 documents that are approaching publication, the VPRF draft, blind signatures, Ristretto, and Frost. So we hope them to occur in the queue in the nearest future. And we have 12 active CFRG drafts. One of them is already in research group last call. That is an additional set of parameter sets for LMS. We hope to have a research group last call for signature key blinding in the near future. And all other drafts are also quite active. And so if you have any questions about the document status or our current work or documents in the IRSG, please speak up. Colin?
Hi, Colin Perkins. If you go back to the previous slide, the VOPRF draft is done. It's just waiting for me to do the write-up and push the button. That'll happen straight after the meeting. Frost, I don't expect any great difficulties. I'm partway through the review, but it's in my queue for straight after this meeting. So apologies I didn't get to it before.
Thank you so much, Colin. Thank you. Any other comments, questions from the room? Nope. Then we'll start with the first presentation. Nick Sullivan.
Okay. Hello. Okay. Hello, everybody. So we've been working at the CFRG for quite a long time now. and we have a lot of experience with the types of documents that come through this research group. It's a unique research group within the IETF, and has some, I guess, unique requirements for writing these. And one thing that we haven't done yet is provide a comprehensive document for advice for authors to help write effective specifications. And so in this presentation, I'm going to talk through a proposal. This is not yet a draft, but a draft that we're considering writing to help authors of these drafts to produce solid documents that are useful as specifications for cryptographic mechanisms. Next slide, please. So there's a lot of text here, but I can just, this is a short talk, I'll walk it through. But effectively what we want this draft to do is to help make sure the quality of these drafts are high. So in particular, minimizing ambiguity and misinterpretations, ensuring that we have consistent and correct implementations that are derived from these specifications. We want to facilitate review and analysis by whether formal analysis or other analysis by cryptographers. And we want to enable the specifications that come from this group to enable standardization within other groups inside of protocols and be interoperable and trustworthy and high assurance. Next slide, please. So when writing a document, I'm just going to go over some of the aspects we want to cover in this document. So if you're going to write a cryptographic specification, especially here in the CFRG, there are multiple audiences, and this is something that we haven't explicitly spelled out as part of the group, but would be very useful and is useful as part of the review cycle. So the three main audiences for cryptographic specifications are implementers. These are folks who are going to be coding and implementing these primitives or protocols. Researchers, these are the folks who are writing papers, either to analyze these protocols, analyze these mechanisms, or come up with new ones, who are looking to have a high amount of trust in what comes out of these specifications, make sure that they match the academic literature. And the last is protocol designers. So this is what's traditionally been the biggest audience for CFRG is the IETF, who have taken the output of CFRG documents and referenced them and incorporated them into various protocols and internet protocols in particular. Next slide, please. And so in terms of presentation, we have some recommendations, some advice here that are pretty broad, but the three main stamps here are simplicity, precision, and consistency. So this document is meant to give advice to authors on how to make sure their documents are have the minimal amount of complexity inside of them so that they can be understood, while still being precise and not having ambiguities. And we also strive for consistency not only within the document, but across documents produced by this group. Next slide, please. Got one, another aspect here is the output of one of these documents is going to, in a lot of cases, be software, or it's going to be used for software, not only just analysis and development of new primitives and protocols, but also it's inside of the IETF, it's going to be useful to be interoperable. So this is a research group in IETF. So there are some general advice that we should provide for collaboration and compromise in developing these documents. Sometimes it hasn't been clear about what recommendations authors have at certain stages of the protocol. So hopefully this clarification will help documents move quickly while efficiently reaching their goal through this process. Next slide, please. This is one example of the specificity that we're going to get into in this document is mathematical operations. So providing specific advice, almost all cryptography is based on mathematics. So there's a couple different points that we hope to drill into in terms of recommendations for representing mathematical operations in an RFC format. Next slide, please. As with most documents that come through this process, security is critical and paramount. So some general advice here for security definitions and threat models, what is to be expected in a cryptographic specification. There's a lot of points here, and all of these slides are on the data tracker if you want to dig in further. Next slide, please. So in summary, with this this document, I'm not asking it to be adopted at this point. It hasn't been written, but this is something for which I want to share with the group ahead of time to see if there are anybody else who's interested in collaborating on this or has strong objections to the idea of putting forward an individual draft with the hope to be adopted to provide a foundation for authors for writing cryptographic specifications with the hope of resulting in high assurance cryptographic implementations and a strong ability to be analyzed by the academic community and to be used throughout the IETF. And so with that, I open it to questions, and I see we have Rich on the line.
Okay, wasn't on. Rich Salzak, I know I'm not a cryptographer, but I may delude myself into thinking I can write well, so I'm glad to help with that aspect of it. And also, I know some other people within my group at Akamai who would really love to help with this. So yeah, and fully support it. It's a great idea.
Okay, thank you.
Kirsty Payne Splunk. Just to say, a lot of this I don't think needs a draft. You could probably get something up a bit quicker on like a wiki page or something, speaking from a dispatch point of view. If you've got newcomers now that don't know some of these basics, you could accelerate some parts of this, put that on a wiki page, and then the more detailed stuff like notation, by all means, put that in a draft.
Okay, thank you. Yeah, that was the original idea, was to use a wiki page, but it started to get so comprehensive we wanted to get through and have more oversight from the broader group on this text. Scott.
Scott Fleur, I'd also like to be willing to help out. One concern I have is what I've seen in a lot of the literature written by cryptographers is they assume mathematics that the average implementer just does not know, and especially how to do it safely. That certainly needs to be addressed.
Thank you. That's a good point.
Joe.
Joe.
Joe Salloway. I think this is a great idea. I'm happy to review, contribute text, whatever.
Okay, thank you.
Daniel Kahn-Gilmore, ACLU, adding my voice to the chorus of yes for this, and I'm willing to help. The mention of test vectors in particular, and if that could include explicit wire formats instead of just the mathematical representations, ensuring to standardizing on an explicit wire format is a really critical thing if you want to get this adopted. Otherwise, the downstream adopters haggle over the wire format forever. So yep. Yeah, this is great work, needs to be done. Happy to contribute.
Great, thank you. Do we want to cut the queue at this point? So everyone who's in, so Colin.
Hi, Colin Perkins. Yeah, I mean, I also think this is a fantastic idea, and I would very much support it going forward. Two things from my point of view as someone who is very definitely not a cryptographer, but who has had to review a bunch of these drafts. It would be useful if it could highlight things to consider when reviewing this type of document. And it would be useful if, one of the things that surprised me when coming to reviewing these types of documents for the first time was that there was no obvious way of going from the pseudocode to the test vectors. And in most cases, if I hunt around, I can find the spec has some code in it, and there's a makefile that derives them all. So I have some reasonable confidence that this is generally correct. But that provenance and that process is often not clearly described in the spec, and it would be useful if it was, if we could provide some guidance for how to do that in a way that enabled reproducibility.
Yeah, that's definitely a very good point, and something that we've seen in a lot of these is checkability or verifiability by non-experts. Chris.
Chris Wood, yeah, in response to I think what you were saying, Scott, there's where papers typically have or make kind of simplifying assumptions about how particular cryptographic things work, like, oh, we have a prime order group, and prime order groups are easy and they fall from the sky, and folks will never get them wrong. Those sorts of things seem like very good opportunities for this group to sort of try to specify more clearly. So in situations where we do find that something is perhaps more complicated than it appears to be at the surface, CFRG should potentially try to embark upon specifying them to make them more clear for implementers. And I think we're doing a good job at that. We're slowly like building from the bottom up with things that are frankly kind of boring, like prime order groups and hash functions and stuff like that. Like, I thought we solved this many years ago, but now we're getting to really more interesting stuff like multi-party computation, which is in zero knowledge proofs. And so this problem is only going to get worse over time. But it seems like a good opportunity for the CFRG to like really kind of bridge the gap between like what's assumed simple in papers and what's actually hard to do in practice. And that's not a comment specifically on this draft, but more on the scope of what the CFRG does.
Okay, thanks, Chris. And
I also love this draft.
And just as a note, the idea for this draft was kind of inspired by Chris's NRW talk 2 IETFs ago. So thank you, Chris, for sparking this idea. Yov.
Yeah, Yovner. So I'm very much in favor of such a draft or a wiki page. It doesn't really matter to me. And there's 2 points that it has to make is about test vectors, not just having test vectors, but having them be comprehensive and cover things that we think are going to be corner cases. The other thing is you have to be very simple and very clear, because the people that are going to implement are not sitting in this room and maybe haven't even read Bruce Schneier's books. So just 2 days ago, I got an email from somebody who's trying to implement Cha-Cha-20 and said, oh, you didn't include a decryption function, only an encryption function. Says, well, it's a stream-like thing. It's like a counter mode. So, of course, the same function both encrypts and decrypts, and he just can't get his mind wrapped around it. So have to be very explicit, and because the audience is not the people in this room, but people who probably have never even been to an IETF meeting.
Thanks, Yov. And we wanted to look at the Cha-Cha draft as an example of some of these principles. And so thanks for pointing out the problem somebody had with it.
Hey, Shivan Sahib, also in favor. I do think that either in a wiki or in this draft, it would be good to put down examples of RFCs that we do think do this well.
Yes.
Because I think that's a really great resource for folks writing new ones to be like, okay, what happened in the past and how can we kind of be inspired from that?
Yes, thank you. That's in the plan. I strongly agree.
Hi, Flo Driscoll. I'll be the 8 millionth person to say I'm strongly in favour of this draft. One thing I was going to say is the aim to have it so that the drafts work for kind of 3 different groups of people, for implementers, for researchers, for protocol designers. I think it's really hard to write one draft that does that, particularly if we're trying to cover like what a prime order group is at every time. So I think maybe using this draft as an opportunity to think about how you tell who a CFRG draft is for might be quite useful.
Yes, and that also lends support to the point of focusing on reusability and referencing across documents and having a cohesive library of these things. So thanks again. Seems we have strong support. Keep your eyes out for an individual draft and mailing list. All right, who's next?
So thank you so much. The next presentation, the editor, key blending for signature schemes. It's about our active work. Please, Ed. Please, Ed.
Hi, great. Are you coming through? Hi, can you hear me?
We cannot hear you, to be honest. Chris, please.
Hi, am I coming through now? Hello?
Yes, now we hear you.
Okay, great. Sorry, very sorry about that.
So please start.
Yes, so I'm Edward. Thanks for allowing me a bit of time to talk about this. This is just a quick note that myself, Tancred, and Chris Wood here have completed an analysis of the draft on key blinding and have uploaded it to ePrint, and it's available there for anyone to go check out, which we definitely encourage. Next slide, please. So to summarize what we've done, so we are looking at security proofs for variations of signature schemes as described in our draft, which is currently on version 3. The schemes are based on ECDSA and EDDSA. And I think one of the main contributions of this paper is we look at have a bit of discussion of the various choices that are possible for security models, and we consider possible configurations of the schemes and how they can potentially be implemented, and how some of those implementation choices can potentially impact security. So it's available on ePrint now for anyone to check out. Next slide. So to begin with, just for anyone who hasn't seen key blinding, it's a very kind of simple idea, but with a lot of subtleties once you get into the details. But the basic idea is you take a key pair, and we'll assume it's an elliptic curve key pair. So the secret key and public key are just an instance of a discrete logarithm problem. And we just imagine sort of taking another scalar b and multiplying it by the public key. So then we have a few sort of key properties of this, which are just with that. If you just have this point capital B, then you don't actually know anything about the original point capital A. But to sign messages, you need the product of A and B. But just capital B is enough to verify signatures. So this kind of provides a way of decoupling the points A and B, except that you probably still need the original secret key to sign. Next slide. So these tend to be used in various anonymity networks. So these are used in Tor. The draft itself is mostly concerned with usage in a rate-limited version of the privacy pass protocol. But the idea is that you have two users who are, exchanging some signed material, and they're maybe possibly being mediated by some server in between who you need to have some sort of anonymity protections from. Next slide. So the interface for key blinding schemes are, we have a typical key generation to generate what we call the identity key pair. And then this is extended with a blind public key operation, which takes a public key and then a blinding key, which is typically just going to be some 256-bit value to obtain a blinded version of the public key. We then sign with respect to a given blinded key, and we also verify with respect to a blinded public key. Optionally, you can also include an unblind operation to undo that blinding operation. And the correctness property here is kind of what you need to have it all work out, which is that if you sign under a particular blinding key and blind the public key under that same blinding key, your signature should verify. Next slide. So one of the interesting things is how the security models pop up here. So the first security property we're concerned with is unforgeability, which mostly bears resemblance to standard unforgeability in that we give the adversary an identity public key, and then the adversary makes signing queries, but the adversary is allowed to make signing queries with respect to a blinding key of their choice and gets back a signature with respect to that message and blinding key that they submitted. And then in the end, the adversary gets to submit a tuple that consists of a message, a signature, and a blinding key. And then the adversary wins if, when you run the verification procedure with that message and that signature and the identity public key blinded with respect to that blinding key, it accepts. You also have to consider a freshness condition, and this is where we actually get some options for blinding that key blinding that you don't have with regular signature schemes. So the sort of basic unforgeability definition would just be that the message has never been submitted as part of a signing query. But we can also extend that and consider, well, what if the adversary maintains the same message, but then somehow is able to modify the signature to work for a different blinding key? So a stronger security property then is something that we might call like a blinding key binding unforgeability. And there the freshness condition would be that if that particular tuple of the message in the blinding key was never a signing query, then this is considered a valid forgery. And then finally, we can add on top of that the sort of traditional concept of strong unforgeability, where the adversary just modifies the signature somehow, and there the freshness condition would be that the signature was not the result of that query to the signing oracle. Next slide. So other than unforgeability, the other main security property is unlinkability, and this is where we're trying to sort of model the anonymity properties of the blinding process. So for this model of unlinkability, the adversary is able to query a blind public key oracle and gets back a blinded public key blinded with a random blinding key. And then the adversary can also request signatures for any blinded public key they've seen. And eventually they are given a sort of real or random challenge where they're either given a new public key or they're given a blinded public key that was either blinded with the same public key that they've been using the whole time or with an entirely new public key that has never been used before. And they're trying to determine which was used for the challenge blinded public key. You can also modify this security model if your scheme doesn't support the unblinding operation by actually allowing the blinding key to be adversarially controlled. Next slide. So to actually construct this, we have two schemes based on ECDSA and ED25519, and it's largely what you expect, except sort of modified to the specifics of the scheme. So for ECDSA, you just hash your blinding key to achieve a scalar, multiply it through by the public key. Similarly for ED25519 with SHA-512, notably, we don't clamp the scalar for ED25519 as we do in key generation, and that's because clamping the scalar can potentially impact the unlinkability property. And then you appropriately modify your signing procedure to make sure that you're using the product of these secret values and using the blinded public key instead of the public key in any situation where you use the public key. Next slide. So in the end, our actual results, like what are our security proofs? We show a proof of unlinkability for ED25519. Previous proofs were sort of Tor specific. This is kind of a more generic proof. We also show a tight proof of the blinding key binding strong unforgeability of the ED25519. There is a couple of previous, there was a tight proof that showed plain unforgeability and a non-tight proof that showed the blinding key binding unforgeability. This is kind of the nicest possible proof, which is great. We also show an unlinkability proof for ECDSA and an unforgeability proof for ECDSA for plain unforgeability in the elliptic curve generic group model. And we also have some benchmarks, and I encourage anyone to check it out. Thank you.
Thank you so much. We have time for some quick questions. Nope. Then thank you so much, Ted. Please, Philip, as an update on VDF.
Okay. Are you driving slides or should I? or I can do it with the phone. So. All right. So yeah, this is an update on the VDAF draft for verifiable distributed aggregation functions. And also a presentation on the paper that we wrote for the security analysis of the VDAF primitives that we were describing in the draft. So this is joint work with Mike Rosulek, Hannah Davis, and Chris Patton. And I would like to thank Chris for lending me his slides for this presentation. So yeah, a little bit of background on what this is embedded in. So in the PPM working group of the IETF, there's currently being standardized a protocol for distributed aggregation of measurements. And that means we want to have functionalities where we can aggregate measurements across many, many clients and only reveal the aggregate results. So this is a sort of multi-party computation setting where we don't want to learn any individual measurements, but only the aggregates across many clients. And applications of that, there are many you can think of. So one, for example, would be COVID exposure notifications, where this is currently being used in the Apple-Google exposure notification in the US to measure the effectiveness of the contact tracing apps. Similarly, you could think of threat detection or performance telemetry and so on in browsers, or ad conversion measurements. So this has a lot of use cases, and that's why these standardization efforts. And the standardization is basically split in two parts. So one is VDAFs, verifiable distributed aggregation functions, which are being developed here in the CFRG. And then DAP, distributed aggregation protocol, which is this wrapper around VDAFs, if you want, that specifies how to run it over HTTP and how the different parties communicate and so on. And that's being developed in the IETF at PPM. All right, here is a high-level overview of what a VDAF is. As I said, we have many clients, think billions, and then just a couple of aggregators. So we might be fixing that to just two, but think of the single or single digit of aggregators. And the way it works, that the client, they have the local measurements. They secret share them between the aggregators, and that's what we call an input share, and then send that out. And the aggregators now can perform an MPC protocol to validate that what the client sent them actually is some valid measurement. And whatever valid means depends on the particular protocol. And after this validation phase, which we also call a refinement phase, the aggregators can locally aggregate all of the shares they got from all of the clients and send the result to a collector who can combine the two aggregated shares and gets the final result. One thing to note here is that this only allows for a particular set of protocols, namely ones where we can compute on each client separately. And then only once we have done all the computation on the clients, we do the aggregation across clients. So this is what we wrote here as this. The functionality needs to be something like f of g of measurement 1, g of measurement 2, and so on. So this is not all of MPC. This is just a very useful particular subset of MPC protocols. And the nice feature that this gives us is that all of the computation is very parallelizable. So we don't need to think about how to shard clients across different aggregator instances and so on, because basically we can just split up the clients and process them in parallel just by design of the protocol. And then how does this fit into the higher level DAP protocol? So that one basically assigns roles to the aggregators. So here we now don't have aggregators that all are equal, but we have a leader who manages most of the communication with the clients. And then we have a couple of helper servers. And of course, in order to satisfy this assumption that the aggregators are not all colluding, we need some encryption that goes through the leader to the helper. But yeah, so DAP uses HPKE for that, HTTP for transport, and yeah, all sorts of business logic also of how to send out keys and so on. So I'm not going to go too much into the details of DAP, but the big question for this talk is, how do we formally define security for VDAFs? So what are the security goals first? And this is taken from the draft. So there are two things we want to guarantee. One is, of course, privacy. That's the main reason we don't want to just measure in the clear. We want to ensure that every client's individual measurement is not revealed besides what's revealed through the sum, through the aggregated output. And the second property we want is robustness. So we don't want a client to poison the result, for example, by adding random noise or by adding some invalid measurement. And yeah, so in our paper, we basically took a stab at formalizing these two properties. And we based that on version 3 of the draft. So right now we are at version 5. So our results actually influenced how the security considerations are written in the draft. And I will also go into that in a little bit. So one issue, for example, that we wanted to solve is how the aggregators basically distribute a so-called verification key that is needed to verify the client's result are correct. This was not really specified before, and through our security analysis, we now have a clear picture of how this needs to be done. And yeah, we also tweaked one of our VDEV protocols as a result, and also improved the round complexity of the second one, which we dubbed Doppler. All right, so you don't have to care about this formal definition here. This is just how it's written in the paper. But informally, we define for the robustness, we define a security game that is basically played between a set of corrupt clients and honest aggregators. Very importantly here, we don't assume robustness against dishonest aggregators. So we assume that the aggregators, they're interested in giving exact results, and we don't care. So if one of the aggregators is malicious and tries to spoil the results, then we don't care, because that's not what we're protecting against. So yeah, in this game, the adversary wins if a collusion of dishonest clients can create a result that does not correspond to an aggregate of a valid set of input shares. And similarly for privacy, here we do care if the aggregators are malicious. So here the adversary controls a subset of the clients and a subset of the aggregators, as well as the collector who gets the final result. So basically we assume just one honest aggregator. And in that setting, we basically, the game is built in a way that we create two sets of measurements for the honest clients that sum up to the same result. And then we flip a coin and choose one of these measurements as the input to the protocol. And the adversary has to choose which one was actually input, right? And if it can decide that with better than equal probability, then the adversary wins the game. Okay, so what is the impact of our paper? Basically, we did revise the security considerations in the draft as a result. One thing that I already mentioned was this verification key. So here we now specify that the aggregators must commit to it before any shares are being generated. Otherwise, clients could do some cheating in that setting. Also, for privacy, the clients must choose a random nonce. And for the aggregation parameters, we have now some constraints on how they can be combined, how a single report from the same client can be reused in multiple queries. Yeah. One quick side note on the formalisms. So as you've seen, we've used a game-based definition here, which is somewhat unusual for MPC protocols. So usually in multi-party computation, you use something that's called the simulation paradigm, where you define an ideal functionality that defines what you want to compute. And then you prove that you can take the actual views of the parties and simulate something, take the input and output of the ideal functionality and simulate something that looks like the actual view in the protocol. The reason we didn't do that here is that we have, for our two security properties, we have very dissimilar assumptions. So one is the corruption model, where for robustness, we assume that both aggregators are honest, whereas for privacy, we cannot assume that. And the second reason is that we want different concrete security bounds. So for robustness, we are maybe willing to take a higher probability of error or a higher probability of a client getting away with cheating, whereas for privacy, we want a really strong security bound. So one open question would be whether this can also be formulated in the simulation paradigm with still producing, usable definition and nice security proofs. All right, and future work. So things that we've been looking into is, can we actually have an automated way of proving secure these kinds of protocols? So Chris gave a talk to the usable formal methods research group here at IETF. And yeah, basically what we would like to have is not having to write another paper for every protocol we come up with, but having some kind of way to automatically proof secure the protocols. And that was it. Thank you very much.
Thank you so much. One quick comment. To be honest, I'm quite happy that the definitions are game-based, because we have people in CryptoPanel that are good with verifying game-based proofs. So at least we can just start reviewing the security assumptions, security models on an early stages. So if you ask us to ask someone from CryptoPanel to verify the models, it will be quite good, and we have the experts. And any comments, questions from the room or from the Meteco? Nope. So thank you very much, Philip. It's a great work. Thank you. Then Tobias Looker, the BBS signature scheme.
Want us to draw the slides? Or yeah, thank you. Can I just indicate when to transition? Okay. Next slide. Yeah, so this is just a bit of a recap of a current draft, which is known as the BBS signature scheme, which in simple terms is a peering-based multi-message signature scheme that supports selective disclosure and zero-knowledge proofs. Next slide. So the first phase, which is the signing phase, allows a signer to sign a multiple or a set of messages and include what's known as a header in our draft. And the header value is something that the prover, the intermediate party, must always disclose, whereas the messages are selectively disclosable by the prover. Next. The next phase is the proving phase, which allows the prover to take a subset of the messages that were signed by the signer and derive a proof of knowledge, a zero-knowledge proof of knowledge of the signature and integrity over proof of integrity over the revealed messages and the header value. Next slide. And then the verifier can validate that back to the signer's public key and learn nothing other than that the prover has a signature on the superset of the messages and also for the revealed header value. Next slide, please. So some updates to this draft. We've recently published draft 3, and one of the issues we were aiming to resolve was how we computed random scalars in the proving phase of this protocol. We were using expand message from hash to scalar. However, that was imposing a limit for us in the context of our draft of 170 signed messages that we felt was insufficient. So we considered a couple of different options. One was arbitrarily calling a C-spring or calling a PRF once and then using the output to compute the n random generators, n random scalars required for the proving protocol. Ultimately, the approach that we landed on was the one in the middle, which is using the C-spring in a loop. We found it to be the fastest option and didn't introduce a new dependency. Next slide. The other update since our last draft is prior to draft 3, we didn't have any proof fixtures or test vectors in our protocol. Next slide. We now do. Next slide. And the issue here was about how we would generate these fixtures in a way that would allow implementers to verify not only that they can verify these fixtures, but they can recompute the exact test vectors. So we had to embark on describing a process around how to mock generation of the random scalars that wouldn't be abused in production implementations, because obviously the scalars in the proving phase being random in production implementations is crucial to the security. However, being able to make them deterministic for the purposes of testing is desirable to improve confidence and implementation correctness. So we invested in, there is now a section in the draft that describes how we do that in the context of those test vectors. And the solution is effectively a single PRF with using the extendable output and using the single seed from those random scalars for the test vectors. Next slide, please. And this is really just talking to how we use that setting, that even the process that we defined for this mocking phase is provided the seed that is used in the test vectors. If this implementation for generating the random scalars was actually used in a production or a live implementation, provided the seed is truly random, say sourced from an RNG, the security holds. These new fixtures have now been cross-validated by multiple independent implementations as well. Next slide. Some other updates that we've made to the draft. We removed the total number of messages required from the input required from the proof of verify API, which has simplified that interface slightly. Effectively, we can deduce that from other parameters that are supplied to that operation. We switched to using C-Spring instead of a PRF throughout the draft. There's also a new academic paper on BBS that will be presented in this year's Eurocrypt that looks at the construction we've been documenting in our draft and has managed to offer some further simplifications and performance improvements. And on the back of that, we've already made some changes through anticipation of that paper being successful in Eurocrypt, and we intend to, as a working group, adopt more of those post this IETF meeting. Next slide. So a couple of questions that we kind of are requesting feedback from the wider group. When it comes to test cases, we have quite an exhaustive list of test cases that include things like bad public keys, manipulated signatures, signatures where messages aren't actually signed by the signer, modified headers and the likes. We've put these in the appendix, but we have had some feedback from implementations that it does make the document quite large, and trying to understand whether or not we should shift them to a separate document, ignore them, pursue a subset. So that is a question. I see someone on the queue.
Daniel, do you want to talk now?
If you want feedback now, or do you want to do it all at the end? Now is okay?
Yes, please.
This is Daniel Gilmore. If you've already done the work of enumerating the negative cases, please do not just destroy them and walk away. They do make the draft much larger, and I don't think there's a problem with having a separate draft that's just the negative use cases separately if we don't want to scare off implementers. But having a zoo of ways it can go wrong is a great thing to produce. So please publish them somewhere, even if not in this one.
Okay, thank you.
Finish your. I can do my question at the end.
Okay.
Mike, do you want to go now?
Okay, I'm Armando. Just a clarification on the dependency with the hash to curve. Are you using hash to fill function or just the span message?
In which part? Sorry.
For generating random scalars.
In terms of our usage of that in the protocol of random scalars, I think my co-editor might be online, Vasilius, who might be able to speak to that. We know in draft 03 we have changed our usage. Just wondering if my co-editor.
Yeah, can you hear me?
Yep.
Great. So for generating mocked random scalars, so just for the test vectors, we are using just expand message. But in the draft as a whole, we have a dependency on hash to curve, and we do also use hash to curve as a function, just not for generating random scalars, if that makes sense.
Okay, thank you.
Mike Elmsworth.
Mike?
So on this negative test cases question, Nick Sullivan, does your draft have an opinion? Like when you're how to write a crypto standard draft, does it have an opinion on negative test cases?
No opinion yet, but something worth considering. I think they do make it larger, and there's opportunity to put test vectors, whether positive or negative, in other places than inside the draft, canonical places. But yeah, no, I don't have advice.
Ori, last comment.
Ori Steele, Transmute. I'm in favor of preserving the test vectors. If they start to become too unwieldy in the current draft, I'm in favor of moving them to a separate document. I think they're really good, and let's definitely not hide them away from implementers. Implementers should be aware of these rough edge cases. Thanks.
Yeah, just to elaborate on that further as well, what we found was sometimes for some of the negative test cases, we would include a reason of why the case should fail. Like this has a public key that is not that of the original signer, or this message was manipulated and those sorts of things. And so sometimes implementations would say, yay, the case failed as is expected, but I'm unsure whether or not it failed for the right reason. And so perhaps a sub-proposal is making that reason somewhat more informational in nature and how it's described, or setting the expectation correctly, so that, in difficult to fail negative cases, that's understood by implementations at least. Next slide. So a map to scalar. So a part of our draft uses this procedure where we take messages and we have to ultimately map them to scalar as a part of the signing process. Currently in the Cypher suites, we have essentially one mapping, which is a hash to scalar operation. However, some usages of BBS can be combined with things like range proofs, where you instead take an integer value and you appropriately map it, and then you can do a predicate operation on it, like less than or greater than. And the question is really where that definition should be. If Cypher suites, for example, the concept of a Cypher suite is in our draft. If a Cypher suite didn't define the mapping processes, arguably it could be vulnerable to bad mapping methods that could be implemented in future. So should we use the Cypher suite layer to essentially define the only map to scalar methods that are permitted for that Cypher suite, and require applications to effectively, define new Cypher suites if you want to use new mapping methods, or whether or not this should in fact be allowed at a mapping level.
Sorry, I don't have the queue put up in time. Chris Wood, don't punt in the application. And just in the name of interoperability, like define it in the specification so that people can agree on how this is done. And it seems like everyone will have a better day.
Cool, thank you. Last one. And then the last one here is point encoding. So the current Cypher suites we're using is defined around the BLS 12381 curve. And the compact encoding or compressed encoding that we're using is effectively a method that is defined by the Zcash community. However, that point compression is curve specific, and effectively we would prefer to use a compressed format because of the terseness of the resulting signatures and proofs. So the question is there a known method of expressing this sort of point compression we should be looking at? We have found one draft that we think could be useful in that regard, or are there any other ideas in how we could express that?
Thank you. Any comments? If you want, we can ask Crypto Panel. You can ask us and we'll ask Crypto Panel. So So thank you so much. The next presentation, it's last about the active work items. Andrei Boshko, properties of AAD algorithms. Andrei, would you?
Yeah, I will try to click for.
Yes, we granted here, and we hear you well, so please start.
Great.
You control
Good
the
morning,
slides.
everyone. Yeah, I can click through slides. Good morning, everyone. I'm going to give an update on properties of AAD algorithms draft and speak a little about some new next steps. Well, since the last IETF in November, the draft was adopted by CFRG, and there were a lot of comments from the community. There was a lot of involvement. Thanks everyone for that. It is very encouraging. So speaking about the draft itself, some new properties were added, and well, the most important thing is that the overall consistency of the draft was rather improved since then. But today I want to speak about some next steps, and well, at this point, a draft is rather theoretical. It might be useful by like cryptographers or RFC writers who want to use some established and common language when writing their documents. However, it seems like it doesn't help those people who want to find an appropriate IET choice for their higher level functional application. So thinking about that, I came up with a short 3-step plan. And the first step is about how to address that issue. And the first step is to add some examples of functional applications for each property, how the property can contribute to a higher level application, and which problems it might solve when using such AET, like, well, you have leakage resilient AET, and functional application is that you can use it on smart cards. Well, it is the first step. The next step is to provide like an inverse mapping from functional applications to properties, so that if you have some requirements, some functional application, you can look it up in that vocabulary and easily understand which properties you need from your AET to fulfill that requirement. Like you want to use your AED securely on smart cards, then you need leakage resistance or resilience. However, I have intentionally missed the step 0. We have to first do some theoretical work and understand what a functional application actually is, how we define, how we formalize functional application, how deep we go in details when we speak about functional requirements and applications. To like demonstrate that it isn't a really, it isn't a very easy problem. Just a short example. You have functional application, like you're an implementer, you want to store, you can't store the whole plain text in a secure memory when you decrypt. It is a usual situation. And you ask a cryptographer, is it possible to do something with that? And the cryptographer will like answer you that you should use a release on unverified plain text secure AET. But actually, with that property, there are a lot of flavors. There is like RUP integrity, there are 2 kinds of RUP confidentiality. So which one actually you need as an implementer? And here's the problem, how to address such rather difficult from theoretical point of view functional applications. There are a lot of answers to them, but they might be very difficult. So in the next episode of the draft, in the next version, the main aim is to answer these questions, to find an understanding how to formalize functional applications and requirements, and how to proceed with the step 1 of the plan. So if you have an opinion on the questions above, or you want to see some functional requirements and applications be covered in the draft, I would be happy to hear from you and chat a little about that. So also, we're going to add some new properties and since it is a draft about properties, and improve the existing one and, well, make the draft more useful. Thank you. I would be happy to answer any questions.
Thank you very much, Andrei. We have some time for comments or questions or discussion. No comments. Thank you, Andrei.
Thank you.
Then the following presentation, Yuta Nakano, OKS. Yuta, please. We'll show the slides, just tell us. Next slide. Please, Yuta.
Okay, thank you very much. Good morning, everyone. My name is Yuta Nakano, and I would like to talk about the update of the algorithm RockIS. Next slide, please. So I have, I think, 3 updates today. The first one is the security evaluation by third party. So we asked 2 institutions, Indian Institute of Technology Madras and University of Rennes, to evaluate the security of the algorithm. And they evaluated in total 5 attacks and confirmed that they're secure against these 5 attacks. And so the IIT Madras evaluated for the differential attack, linear attack, and forgery attack. And University of Rennes 1 evaluated adding the 3 attacks by the IITM and integral attack and the state recovery attack. Yes. Next slide, please. The second update is the new security claim about the key committing security, which is the property that ciphertext can only be decrypted with the same key that is used to encrypt that plaintext. So, for example, if the plaintext is encrypted with key K1 and generated the ciphertext and tag, then this ciphertext can only be decrypted with K1. And if you try to decrypt with different key, K2, then it cannot get any output from the ciphertext. And RockIS provides 128-bit security, key committing security. Yes, and next slide, please. And the third update is the performance variation. So in November, I showed the performance test result on 12th generation Intel Core i9 processor. And this time I did the variation on 3rd generation Core i9 and also Ryzen 9 series. And performance compared with AS256 GCM is as shown in this graph. So on Core i9, RockIS can perform more than 220 gigabits per second, while AS is around 60 gigabits per second. And on Ryzen, RockIS is around 210, and while AS is around 110 or 20. Yes. And difference between these two on AES is because of the support of the instruction set on the Core i9 series and Ryzen 9 series. Yes. And next slide, please. And finally, we published the implementation as an open source, and now it's available on GitHub. So please feel free to use the implementation and embed it in your application protocol or anything. And if you have any feedback, I'm more than feel welcome to receive. And yes, that's all. Thank you very much. If you have any questions or comments.
Thank you, Yuta. And moreover, if you have any comments from your side to the AAD property draft, so please help us, because we want the draft to be as complete as possible.
Yes.
And any questions or comments to Yuta? No questions, comments. Thank you so much, Yuta.
Thank you.
The following presentation goes Amjad, RSA blind signatures with public metadata, 10 minutes. Do you want us to share the slide or your request?
Okay.
Yes, we've granted. I think that you can control the slides.
Oh, which one is it? Toward the end.
Yeah.
So please start.
Hello. Okay. Yeah. So, hi. My name is Goss, and I'm presenting on partially blind RSS signatures based on a draft recently put out. This is a joint work with Scott Hendrickson, Christopher Wood, and Kevin Yeo. The names are in alphabetical order. So, basically, I'll go over some motivation for blind signatures, for partially blind signatures, as well as for RSA blind signatures. Then I'll quickly go over what RSA blind signatures, give a little bit of background on them. Then we'll talk about partially blind RS signature, which are basically blind RSA signatures with public metadata, and which is basically the meat of this talk. Quickly go over the benchmarks for our implementations and basically the current status of the document, the implementation, and basically where do we go from here. So blind signatures are pretty motivated at this point. They're used in Privacy Pass. They're used under the hood in VPN by Google One, in iCloud Private Relay. They can be used to avoid repeated captcha solvings, for private click measurement, for Tor denial of service defenses, and the list goes on. Partially blind signatures, basically, I'm going to use it interchangeably with blind signatures with public metadata. They are also have a fair share of motivation. A recent draft on verifiable oblivious pseudorandom functions, they have an oblivious variant. So it's natural to think of blind signatures with a partially blind variant as well. These signatures can basically be thought of as signatures for specific settings. For example, these settings could be geographic locations. Like if I want a signature with Japan as Japan in public metadata, I also want them to only be cryptographically verified with Japan in public metadata and not for some other country. One can think you can have, you can have different keys for different metadata, but the issue with that is that you have to sometimes have to fix the choices of public metadata ahead of time, and key management scalability concern can be very bad in production services. Yeah, so but for blind RSS signatures, recently IETF adopted a document for this. And the reason was that it's a simple one-round scheme and it's a stateless server issuance for the signatures. And also they're publicly verifiable and have a widely supported implementation for that in different cryptographic libraries. So it's natural for us to think of a public metadata support for the standard as well. All right, so I'll quickly go over what blind RSS signatures are. They basically work as follows. You have a client and a server. The server has a public key and a secret key. And the client has, let's say, a message that it wants to get blind signed. It asks for the public key from the server. The server will basically, the client will use the public key and the input message, pass it to a blind protocol, and produce a blinded message, which it will send back to the server. The server will then use the blinded message and the secret key to produce a final signature. So produce a blinded signature and send it back to the client. The client will then use the finalized protocol. Using the public key, the message, the blinded signature, and the inverse it generated earlier, and produce a final signature. A couple things to note here is that in the finalized protocol, public verification is run as a subroutine to make sure the signature is correct. And this signature, again, is publicly verifiable because it only needs the public key to verify it. Moreover, the input message is not directly blinded. It is first passed to some, it's encoded first, and the standard proposed PSS encoding for that. Sorry. All right, so how do we enable partially blind signatures? We basically make sure that we use the same public metadata in all stages of the protocol, blinding, signing, finalizing, as well as verifying. The exact changes are that before you blind your input message, we augment the input message with the public metadata and then pass it to the PSS encoding function. Secondly, we also augment the public key, which is basically we take the public key and multiply it with a function of the public metadata. The function here is we are using HKDF for ease of implementation. The technical challenge here is that HMD needs to be co-primed to phi of n, where n is the RSA modulus and phi is the Euler-Stoichhian function, in order for the server to generate the correct signing key. And in order to do that, in order to solve that challenge, we basically put a restriction on how the RSA modulus is generated, and we only use RSA modulus which are product of two safe primes. How that helps us to do that is in the draft, and it's little. I can't go over it in 10 minutes. All right, so we vetted our protocol in multiple ways. We have one more unforgeability proofs for the protocol, which is basically that if I ask a server to give me n signatures on random data, I cannot forge an n+1 signature. We have an unlinkability proof for the same public metadata, which means that if I have two messages, I get under the same public metadata and I get them signed by the server. And the server produces two blinded signatures. And then I run the finalized protocol and convert those blinded signatures to final signatures. The server will not be able to tell which of the final signatures were linked to which blinded signature under the same public metadata. We also took care of domain separation in our protocols. We ensured that different RSA moduluses and the same public metadata would lead to different public keys, augmented public keys. We also made sure that hash functions in the input message and the hash functions used during public key augmentations were domain separated using standard techniques like putting tags in the input to the hash functions. Moreover, we are aware that as our public keys are non-standard sizes, there could be non-standard sizes because of the HMD here. We put caveats and mitigation techniques for denial of service attacks in the draft. Finally, we have some benchmarks for some implementations. We have the left column has the numbers for the standard blind RSA signature scheme, and the right column has the numbers for partially blind RSA signature schemes. You can see there's an overhead, but we hope to see this improve as the code becomes more optimized. We have two implementations right now, and I have linked them below. And I thank Christopher Wood for providing the second implementation in Go. And finally, for current status, we have two implementations right now. One is in C++, one is in Go. It solves the need for privacy. This draft solves the needs for need in privacy pass for this type of token and this type of signature and other real-world applications. We have a draft out. We have an academic paper with security proofs to be put out soon. And basically, yeah, what's the interest in adopting this document? And thank you.
Thank you so much. Any comments or questions now? If not, could you please? Oh. David, please.
Hi, David Skenazy, crypto enthusiast. Ooh, that's terrifying. I'm also at Google, but different parts of Google. So when we talk to each other, it's through the IETF. We actually just met for the first time here. I just wanted to say we're interested in using this for our IP protection service in Chrome that we're working on this year. And we'd love to see this progress at the IETF and get the amazing level of review from this group. So I personally supported adoption.
Thank you.
Scott? Scott, please.
Thanks for presenting, Gauss. I also work at Google with David and both Gauss. Sometimes I'm the intermediary between them. I've posted a draft that uses this protocol for a privacy pass variant that incorporates public metadata. And I'm a strong supporter of adopting this draft into the CFRG and continuing work on it. Thank you.
So I think there's quite an interest in the draft. So please, could you please bring it to the list and call for adoption?
Yeah, okay. Right. Thank you.
Thank you, Gauss. The next presentation, Dimitris Mouris, Plasma, VDF-related protocol.
Hello.
Do you want to control it, or do you want us to?
Yeah, I have some animations. Actually, can I share my screen?
Yes, you can control the slides. One more time.
Oh, you want to share your screen, right?
Could you please request it once again?
Yep.
I think you requested twice. Now your screen is being shared.
Mm-hmm. All right, perfect.
Yes, we can see the slides. Please start.
Okay. Yeah. Hello, everyone. My name is Dimitris Mouris, and today I will present to you my joint work with Pratik Sarkar and Nektaris Toutsos on Plasma, a framework for private and lightweight aggregate statistics against malicious adversaries. So we will focus on the problem of private heavy hitters, and this is a VDAF-related protocol. The problem of heavy hitters essentially focuses on computing the most popular client submissions without revealing each individual submission. The prominent work of Poplar addresses this problem using two servers that are assumed to not collude with each other. And the threat model of Poplar protects the correctness of the protocol against malicious clients and also the privacy of the honest clients. So in this setting, we can see that we have multiple clients, and some of them might try to behave maliciously. And Poplar addresses that by running some MPC checks and rejecting everything that's not well-informed. Unfortunately, if we have a malicious server, the malicious server will be able to introduce some additive errors to the protocol, and the honest server will not be able to detect this. Although the honest client's data will still be protected, the output of the protocol will not be correct. We solve this issue with Plasma by introducing a third server, and our threat model protects both correctness and privacy against both malicious clients and the malicious server. So instead of using MPC checks, we protect against malicious clients using a new primitive called verifiable distributed point functions, or VDPFs, that essentially, instead of running these expensive MPC checks, it only relies on some lightweight and symmetric key primitives. Finally, to defend against a malicious server, we have introduced a third server in the protocol instead of using just two, and the two honest servers are able to detect any malicious activity. So let's quickly see how DPFs work, or distributed point functions, because they're the backbone of both our protocol and also the protocol of Poplar. So we have a client down here. Client down here, and essentially this is a binary tree where it's everywhere 0, except for a specific path that's ones. Now all the leaves of this binary tree essentially are all the is the domain of all the possible bit strings that the client can have. And this one down here represent this client's private input. The ones that are above it essentially represent substrings of this private input. Now, what the client is doing, and that's an interesting part about DPFs, is that they create two keys instead of secret sharing the whole binary tree. They just secret share. They just send two keys and some auxiliary information to the servers, and the server can use the keys and the auxiliary information, which I'm not showing here, to expand and generate these the secret shared trees. So as you can see here on blue, we have additive secret shares of 1, and everywhere else we have secret shares of 0. Now we will repeat this process for multiple clients. Each client sends their keys, the servers expand on them, and then they aggregate everything together. And at the end of the protocol, they just merge their data, and what they get back is the final aggregate statistics. So this is too good to be true, because a malicious client can just double vote, and by double voting I mean that they can introduce more than one paths or more than one leaves that have non-zero values and vote for multiple points. And because these are shares, the servers do not have an easy way of detecting that. A malicious client can also do a disproportionate voting attack, meaning that they can create some shares that when they add up, they are neither 0 nor 1. Again, the servers do not have an easy way of detecting that. We defend against these two attacks by using verifiable DPFs. And quickly about a few things about our notation. So here we have the two keys that I mentioned before that the client sends to the servers. We have a private point A, and we also have a public vector X. So this vector X is essentially all the domain that each client's input can be within this domain essentially. And A is the private point that exists somewhere in this domain. So X is publicly known to the servers, and A is private to the client only. Now the client generates these two keys, and the two servers can evaluate on the public domain the key. So server 0 is evaluating with key 0, and server 1 is evaluating on key 1. And they get these capital Y and capital Z, which are essentially some vectors. And the form of these vectors is this one, where we have a secret share of 0 everywhere, except for a specific point where we have a secret share of 1. And the correctness of VDPF essentially guarantees us that if we add up these vectors, we'll get a one hot vector where it will be everywhere 0, except for a specific point that it will be 1. And that point essentially will be the 8th point, which is the client's private input. Now, about the verifiability property, when we have this evaluation, apart from this secret shared vector, we will also get two proofs, P0 and P1. And if these proofs are equal, that means that the shared vectors Y and Z are well formed, which means that essentially if we add them up together, they are everywhere 0 except for a specific point. Now, this does not guarantee us that the non-zero point will be 1, but at least it guarantees us that we have just one non-zero point, which will solve the double voting attack. Now, to also check that this point is 1, what we can do is that we can sum up all the elements of this vector together and hash them, and check that they are equal to the hash of 1 minus the addition of all these elements. Now, with both properties together, we can tackle malicious clients, and we defend against the double voting attack by the verifiability property of the VDPF, and we defend against the disproportionate voting attack by these hashes that I just mentioned. Next, let's see what a malicious server can do. So if we have an honest client and they just secret share their tree, a malicious server can easily introduce some additive errors to the computation. This means that they can just add something to the result, and because this is local to them, the honest server does not have an easy way of figuring that out. And at the end, when they reveal their results, the honest server will not be able to detect this, will not be able to detect that the malicious server has added something there. And previous works are vulnerable to this problem, or rather to this attack. So we solve this by introducing a third server. And we rely on replicate secret sharing. So the two honest servers are able to detect that the third server is acting maliciously. Finally, we introduce a client batch verification check that uses Merkle trees. And essentially, this allows us to very quickly verify if we have some malicious clients and easily find them and remove them from the protocol. So down here with sys, I have the clients, each one like locally to the server. So these are the client data. And we build two Merkle trees. And then the servers check the Merkle roots. And since these are different, then we check the left subtree and the right subtree. Since the left subtrees are equal, then we don't have to go down essentially on these trees, and we can just check it recursively the right subtrees until we find the clients, the malicious clients, and then remove them from the protocol. And the nice thing about this is that if we don't have any malicious clients at all, this is just one hash that we're checking. But in the presence of malicious clients, both communication runtime depend on if we have malicious clients or not. But this check essentially depends logarithmically to the total number of clients. About our experiments, we compared with Poplar for up to 1 million clients for bit sizes of 32 up to 256 bits. And we observed a 3 to 6 times speedup. And finally, due to our batch consistency check, we see significant communication benefits over Poplar, but this is for honest clients. That's all. I'd be happy to answer any questions.
Stanislav Mishlev. Dimitris, thank you very much for the presentation. We have three questions. Please, Philip.
Hi, Philip Schoppmann, Google. Great talk. So I like the verifiable DPF a lot and the fact that you can do that in a single round. So what I presented before, the Doppler protocol in our paper, I think yours is basically a better version of that if we just take it in the two server setting. So I think this, would fit very well with the VDEV draft. I have a question on the verification slide. Could you go back to that?
Yep, which one?
The one where you show the vector that has a single non-zero.
Oh yeah, sure. Right.
Yeah. So with this hashing at the end, what happens if the servers don't evaluate on the point that is 1? So if we only have zeros, does it still work?
So the client just submit everywhere zeros, you mean?
No, the client submits a 1, but it happens to be not a heavy hitter, so we don't explore that part of that part of the tree where there's a 1.
Oh, I see what you're saying.
That makes sense.
Can I answer the question?
Yeah, sure. My co-author Pratik is here. Yeah, Pratik, jump in. Sure.
Hi, Philip, can you hear me?
Yes.
Yeah, so this is the VDPF. So here we only consider like just the leaf level comparison. For the verifiable incremental DPF, when we consider like heavy hitters, we have to consider that the root and the each parent and their children have the same values. So that's a more local check. So that's taken care. Like you can check that the children have the same value, which is coming from the parent, and you can repeat that check. And that's also local. That also can be done efficiently.
Got it. Okay, so that's not for the heavy hitters. You're not doing this check here, but you're doing this parent
No, this is for the histogram actually. Like due to time constraints, Dimitris couldn't talk about the VIDPF, which is the verifiable incremental.
So essentially, this verifiable DPF primitive is from another paper. This is not what we introduced. So up to here, this is from a paper from Leo De Castro and Taglioni Polihroniadou. But what we introduce on top of that is the verifiable incremental DPF that also uses the tricks that Poplar is using to be able to do that for each level, and you don't have to do this like multiple times. So essentially, you can have a state from the previous level and then build from that to go to the next level. And we just use the trick that Pratik mentioned, that when we have a path, let me actually find the tree. Yeah, when we have a parent here, we check that these two leaves have the same essentially counter as the parent.
Okay, I think I get it now. Thanks.
Okay.
Tim, please. Tim, you're next in the queue.
Yeah, sorry, just waiting for my mic to come on. Yeah, hi, Tim Gagan, Internet Security Research Group. In particular, I'm one of the editors of the DAP draft in PPM. So I'm interested specifically in the dimension of your scheme where there's an extra aggregator server that provides more resilience against like one defecting aggregator. So the way you put it was that adding the extra aggregator solves a problem. I think it's more apt to say that like it picks a different trade-off. So here's the thing. Yeah, obviously you get more resilience against a defective aggregator, but on the other hand, if you have one more server involved, it's much more expensive to run and much more complicated to coordinate the communication, right? So I don't bring this up like just to criticize, but rather because currently the DAP editors, we have like committed as of the PPM session back on Sunday, or sorry, that was Monday, Japan time. We've committed to taking a change to DAP that would restrict that protocol to exactly 2 aggregators, right? Which I think would rule out that part of Plasma, though the other part of Plasma that's like a faster DPF is still very compelling. So, all right, the reason I bring this up is that, our reasoning is that, in this space of trade-offs, we're choosing to optimize for operational simplicity and performance of the protocol. So what I'm curious about, for the room really, is that, are there people out there who are considering deploying DAP, considering deploying something like Poplar, who are concerned about the sort of one defective server attack that this mitigates? Because if you are, please let us know in the PPM working group so that we can, reconsider the change that we're about to make to DAP. And I had another observation which I forgot, so I guess it couldn't have mattered. Thanks very much.
Before you go on to your next one, thank you so much for the comment. Yeah, well, that's totally correct. And what we are actually doing is that we run, because we have 3 servers, we run 3 sessions total. So for the client, there's also some more communication that they have to send. But apart from that, we have a trick to essentially the 3rd server can replicate locally what the other servers are doing to try to optimize this a bit. And even in the presence of these, and also like the more session that we run compared to Poplar, we saw some performance essentially advantages.
Chris?
Chris Wood, yeah, I think Tim said exactly what I kind of wanted to say at the mic. However, I just want to pile on that it's not necessary that whatever decision you happen to make with respect to VDAF, like maybe you do pull this into VDAF and introduce a new particular type of primitive that requires or does allow, a 3-party non-colluding solution. That doesn't mean we have to actually implement that and support that in DAP. It could be the case that in DAP, we restrict ourselves to exactly 2 aggregators that are non-colluding. And then if someone wanted a different protocol that did require 3 different non-colluding parties, we could go off and separate or specify that separately. So I don't know if we need to answer this right now in the DAP world. And because I don't think we need to answer it right now in the DAP world, I think it's reasonable to continue perhaps investigating how we might merge this into the existing VDAF work on the basis of the benefits that you described in your presentation. I guess that was more of a comment to Tim than to you. But hey, Tim.
Sure, thanks.
Thank you. We can continue the discussion on the list. Thank you, Dimitris. And the final presentation for today, my contours, chem combiners. Please, Mike. The last one.
Hello, Mike Ellsworth. Hopefully this will be quick. This is a lot less deep than the talks we've just had. Hopefully it's this is a quick pass through. Next. So the basic point here is post-quantum hybrid chems are starting to show up in all sorts of places. There's lots of protocols that want to take a new thing and combine it with an old thing. Here's a couple examples: the TLS hybrid design draft, the LAMPS PQ composite chems for CMS and SMIME, the OpenPGP PQC draft. I've got the IPsec one in brackets because it's not really strictly a one-shot hybrid chem, but it is a hybrid chem. And I'm sure there will be more. I'm sure this is not going to be the exhaustive list of things that need to do hybrid chems. So I'm proposing that CFRG should standardize a known, safe, super strong, good combiner. If you want to combine chems, this is a really strong way to do it. Next. So the goals of this draft, trying to target a similar goal to HPKE 9180 in that we're specifying a really strong construction. If you use it, it's known good. There may, of course, be ways to simplify it. There may be cases that don't need a construction that strong, and that's fine. So the TLS hybrid design draft and the OpenPGP PQC draft are both opting to use a simpler combiner, and they're specifying we've got stronger assumptions on our input chems than the general case, and therefore we can get away with a simpler combiner. But our goal here is to say there are hard cases. In particular, CMS SMIME is a hard case. We still support RSA chem. It's static long-term keys. You may well have servers acting as decryption oracles for those long-term RSA keys. That's the hard case. Let's specify a combiner that, handles it properly. I'll also point out from a hallway chat yesterday, Paul Hoffman made a suggestion that this draft here in CFRG could act as a bit of a living document and try and create an appendix that categorizes weaker or more special purpose combiners. And maybe we could try to make some sort of table of security assumptions that they made about their input chems and why that allows their combiner to be secure in that context. Maybe this draft could be the place to collect that. Next. So that brings us here. I'm writing the hybrid combiners draft for LAMPS. Aaron is writing the hybrid combiners draft for OpenPGP. We need this document to exist. We need a strong reference to motivate why we're combining our chems the way we are. Speaking for Aaron and myself, I think I do not speak for Stavros, but speaking for Aaron and myself, we don't feel qualified to write this draft, but we needed it to exist. We needed it to exist now. So we went ahead and wrote it. And we're operating in this mode: write the draft, wait for people to yell at us on list, take their feedback, make it better, conquer the world. And we're already at round 3 of this iterative process. And I think what we've got now is a much stronger combiner than what we had in London. So process working, yay. Next. So here's the actual crypto. In the current form, what we're proposing is actually a slight improvement or a slight strengthening of the NIST SP 856CR2 multiple input KDF. So the construction at the top essentially is 56CR2. The improvement is that the KIs are actually a hashed concatenation of each shared secret with its corresponding ciphertext. And that's the bit that I think is being simplified out in various other drafts, that you don't necessarily need that inner hash. And that comes down to the details of whether your input shared secrets are fixed length. That comes down to whether your input chems are in CCA2. If not, I think you need that extra hash in general, but if you have strong assumptions about what chems you're going to be using, you might be able to drop it. We're also proposing here instantiations based. These are all SHA-3 based instantiations, which is a open point of question. Do we want SHA-2 based for performance reasons? But here we're specifying 4 instantiations, which are all SHA-3 based. And then, yeah, the fixed info allows it to be fully compliant with the NIST KDF. And, you know, if you have protocol domain separation information, here's a spot to slip it in. So that's really all I've got. That's it. Please yell at us on the mailing list. If you yell usefully enough, I will make you a co-author. So yeah, is this useful work for CFRG to take?
Thank you, and we have some time to discuss it. Please, Deb.
Quinn Dang at NIST.
I think Deb is remote.
I'm sorry?
First in
Can you
queue.
hear me now? I was having trouble coming off of mute. Can you hear me?
Yes. Yes.
Oh, there we go. So I was going to ask you why SHA-3 as opposed to SHA-2. Is there a reason? Other than it's shiny and cool? And possibly not faster?
I think so. There was discussion about that on list. Aaron and Stavros have been taking the questions about that. So maybe ask that in chat. I think Aaron at least is online.
Okay, that's my only question. I mean, it's
I think
shiny and cool, but
in one version of the draft, we did have an SHA-2 HKDF construction, and then after some debate, we took it out. And I'm sort of the wrong person to justify why, so I'm not going to attempt to do that on record.
Okay.
Thank you. Richard Barnes.
Answer this question. It's the reason why we opted for SHA-3 is because of the construction that allows us a simpler proof to define it a PRF that can be keyed by any input. SHA-2 would require probably some more complex construction like the one proposed by Nimrod. And this is why we propose to have only SHA-3 candidates into at least the CFRG draft. Then if someone wants to deviate from that and wants to have their own implementation using SHA-2 because they can prove that their security model is strong enough, that's probably the way to go, at least in my opinion.
Thank you. Douglas?
Douglas Stabila. I wanted to say that we'll take a look at trying to prove security of these and I guess try to differentiate under what conditions on the different like hash functions and KDFs yield security with that combiner versus the TLS combiner. Thank you.
Thank you. Quinn?
Quinn Dagan, do you mean the CT sub I is a ciphertext? Is that what it means?
Go back to the construction slide.
Is that what it means in the draft?
Yes. Yeah. Well, yes. Yes. So SS sub I is the shared secret, and the CT is its corresponding ciphertext. Yes.
Potentially, some chem or chems in the future, they might not generate the shared secret from the ciphertext, and the ciphertext, you know, potentially for some chems can be very large. So I don't think putting the ciphertext in the next step for the KDF is a needed thing to do and potentially create some performance problem.
Yeah. So again, this was added, I think by Stavros added this change in order to prove in CCA2, like the chosen ciphertext attacks more, or proof is more tight if you include the, I don't know the details, but it is in our security consideration.
Yeah, for the security for CCA2, you need to look to Pacific Chem to see how the transform happens, and the proof is going there, and the KDF is the later step, because in the chem normally it has a KDF in there to generate shared secret already inside the chem.
Not RSA chem, at least that the KDF is external to RSA chem.
So that what I'm saying. The security is different thing for the KDF over here, basically you want to generate more keys than the one key coming out from a chem. And so I'm just saying that CTI could potentially have some problem for the performance reason. And also, what is H over here?
H is a hash function. So we have in the instantiations there, we have KDF and H both defined. So in the first instantiations, they're both SHA-3, but in the second instantiations, KDF is a KMAC and H is still SHA-3.
No, because okay, so we don't list it here, the H, but we list the KDF. That's why I'm asking.
Sorry?
Oh, on the slide, we listed the KDF instances, but we did not list what H is, what the option for H.
It's right after it.
The right after that. Okay, sorry.
May I just say
something?
So for the two questions, why are we using SHA-3? It's, well, we rely on the random oligo properties of Ketchak. And it's not because it's shiny and cool and new. And for the second question, if the ciphertext has to be present in the combiner, so we are also heavily relying on the ciphertext to be present because we are building up from a work of Giacomo, Hoyer, and Pöttering that include the ciphertext to mitigate decapsulation oracles. And they say if you do that, then the complete construction is CCA2 with at least one ingredient chem is CCA2. So this is the reason why we include the ciphertext there.
Thank you.
Yeah, as I said the chem, whether or not it has a CCA security 2 or not, it depends on the details of the chem. The KDF is, this KDF is outside the chem, so it's kind of different.
Yes,
So
but
what
the
we-
idea is to have a chem a chem combiner that takes chems that might take an ingredient chem that is not CCA2 secure. Yeah.
Oh, okay.
And
So
still
you
combine it with another one, like the ones from the PQ standardization process
chem.
right now.
Okay.
Then it
Okay.
it preserves CCA2.
Okay.
Yeah,
Okay.
if you have one input chem which is in CCA2 and one which is not, you want the combiner overall to be in CCA2. Preserve that property from a single of the inputs.
If the non-CCA security chem for CTX and you has like this, it has some benefit, but it has security proof to look into this to see if it actually have CCA security from this kind of construction from the non-CCA security chems. So yeah, if that's what we want to gain more security, and that seems okay, but I'm not quite sure if that would achieve CCA security. I haven't seen a proof for that from a non-CCA chem.
Please, Russ.
Hi, Russ Housley. I'd like to speak in favor of this work and getting it done as quickly as possible, because we're kind of at a place in time where we have an opportunity for a lot of crypto libraries to have a few primitives that are used by all of the protocols. And we need a construction where if we have one good input, we get the best of the properties that went into it, even in the face of aging crypto algorithms where maybe we thought it had CCA2 and then later somebody proves it didn't, or somebody registers in IANA some algorithms that are not as strong as we would personally like, but they're going to get used. So let's get the best we can out of the inputs. Thank you.
Daniel Gilmore. I just wanted to say that I would love to have the CFRG's eyes on this. Please do adopt this. From the OpenPGP working group, we are probably going to recharter, hopefully. And if we do, I'm quite sure that the PQC stuff will be in, and we're going to need guidance like what is being proposed in this draft. Thanks.
Thank you, Scott.
Just a quick nit. I don't believe that we can always say that the output size is limited to 256 or 512 bits. There may be some cases which actually generate several symmetric keys from the same CAM input. It may be wise to replace SHA-3 with a shake.
This is being addressed with the KDF construction that use KMAC that allow an unlimited output or almost unlimited. As well, the SHA-3 constructions have the counter that can be increased and rehashed to generate as much key material as necessary.
Thank you. Please take it to the list. I think that people will need to discuss it, and maybe we'll discuss the adoption of this document on the list. Thank you so much. And now it's the AOB, any other business, and we have at least one question, one item from Dan Hawkins. Dan, please.
Yeah, thanks, Dan Harkins. I was going to get in the queue, but you just mentioned me. So I have a draft in CFRG on doing some extensions to HPKE, specifically for adding compact output to the NIST curves and also a deterministic cipher for key wrapping. Watson recently on the list proposed adding another feature to HPKE for doing HMAC and AES-CBC. I don't know whether the group thinks that that's a good idea or not, but if they do, it would probably make sense to add that to my draft and just do it all together. I know that we're adding a whole bunch of new features to something that already has too many features, which is probably not good. But if there is a strong desire for HMAC and AES-CBC, then please speak up on the list. Thank you.
Yes, Scott.
I've been going over the partially blind RSA signatures, and I think I see a cryptographical weakness. If the hash of the metadata happens to be a large prime times a smooth number, it sounds like anyone should be able to generate a signature for that metadata, assuming they can get signed by any metadata without the signer being able to validate that. That sounds like maybe 1% of all possible metadatas can be forged.
Any replies or comments?
I'll put that on the list. Yes.
Yes. Thank you. Thanks so much. Any other comments, questions, proposals? We have some time left, surprisingly. Florence?
Hi, Flo Driscoll again. So this is just well, I'm sure most people know that PQIP is in the next session. I have a draft there on terminology for post-quantum hybrids. I wanted to flag it to CFRG because when we proposed this at Sec Dispatch at IETF114, the room was kind of split between dispatching it to CFRG or dispatching it to a new group that didn't exist yet, which is now PQIP. So if people are interested, please come. If you like arguing about mathematical terminology, which I'm sure isn't something which applies to anyone in this room, then yeah, come along or have a chat or speak about it on the mailing list. Thanks.
Thank you. And then we'll finish our meeting. Thank you, everyone. Thank you for coming. Have a nice day.